Okay, so the equation is called an analytical or closed form solution because it exactly satisfies the original differential equation. Unfortunately, there are many mathematical models that cannot be solved exactly. So in many of these cases, the only alternative is to develop a numerical solution that approximates the exact solution. Numerical methods are those in which the mathematical problem is reformulated so it can be solved by arithmetic operation. So again, this can be illustrated by our original equation, which is dB over dt equals g minus c of d over m multiplied by b squared. Recall that dB over dt, so we all know that dB over dt is equal to the limit of change of b over change of t at delta t approaches, or rather is equal to 0. So delta b over delta t is equal to b of t sub I plus 1 minus b of t sub I all over t sub I plus 1 minus t sub I, where b and t are differences in velocity and time computed over finite intervals. So which is b of t sub I is a velocity at initial time t sub I, and b of t sub I plus 1 is velocity at some later time t sub I plus 1. Okay, so the use of finite difference to approximate the first derivative of v with respect to t. So with our equation, which is b sub t sub I plus 1 minus b of t sub I all over t sub I plus 1 minus t sub I is called a finite difference approximation of the derivative at time t sub I. It can be substituted again to give I b sub I b of t sub I plus 1 minus b of t sub I all over t sub I plus 1 minus t sub I is equal to g minus c of d over m multiplied by b sub t sub I quantity squared. So this equation can be arranged to yield, so the final one is b sub t sub I plus 1 is equal to b sub t sub I plus our original equations multiplied by t sub I plus 1 minus t sub I. So again, notice that the term in brackets is the right hand side of our differential equation. So we can now see that the differential equation has been transformed into an equation that can be used to determine the velocity algebraically at t sub I plus 1, using of course this slope and even of course the previous values of b and t. So if you are given an initial value for velocity at some time, which is t sub I, you can easily compute velocity at a later time, which is t sub I plus 1. So this new value of velocity at t sub I plus 1 can in turn be employed to extend the computational to velocity at t sub I plus 2, t sub I plus 3, and so on. So this approach is formally called Euler's method. So we will discuss that one into a more detailed when we turn to differential equations later in this problem. Okay, let's proceed to the numerical solution to the bungee jumper problem. So perform the same computation as in example before, but in this case use our equation, which is b sub I plus b of t sub I plus 1 is equal to b sub t sub I plus original equation multiplied by change in time. Okay, so let's compute of course the velocity with Euler's method. So let's employ a step size of 2 seconds for the calculation. So at the start of the computation, t sub 0 is equal to 0. So therefore, the velocity of the jumper is 0. So using this information and then the parameter values from our equation, you can use that one to compute, of course, velocity at t sub 1 is equal to 2. So by direct substitution, b is equal to 0 plus quantity 9.81 minus 0.25 over 68.1 multiplied by 0 squared multiplied by 2 is equal to 19.62 meter per second. Okay? So for the next interval from t is equal to 4 seconds, so the computation is repeated with the result. So b of 4 is equal to b of 2 plus g minus cd over m multiplied b of 2 quantity squared. Of course, we have one step size of 2, which is 4 minus 2, resulting, of course, of 36.4137 meter per second. So the calculation is continued into a similar fashion to obtain, of course, additional values. Okay, so the results are plotted in our graph. So along with the exact solution, so we can see that the numerical method captures the essential features of the exact solution. However, because we have employed straight line, so to approximate a continuously curving function, so there is some discrepancy between the two results. One way to minimize is such discrepancies is to use a smaller step size. So for example, applying to our equation at 1 second interval, so in a smaller error as the straight line, so that is